Let's wait for the experiences to show.
Eight angles along this one.
We have one.
Oh, we can pretend to be experienced.
I'm sufficiently engineered.
You're engineer.
Numerical experimental.
Yeah, sure. We play with data too, right?
And with error bars.
Mm-hmm. Oh yes, giant error bars you'll see in a moment.
Okay, yeah, thanks everyone for coming. We're very happy today to have John Karpie, who's visiting us from Jefferson Lab, where he's a postdoc and soon to be the Nathan Lee School Fellow starting in October, right? Is that right?
Mm-hmm.
Okay, before that, John was at Columbia University as a postdoc, and then before that, he was a graduate student at William and Mary, working with Costas Ordinos and other people in the group. And he has done a lot of different work regarding PDFs and how to get PDFs and GPTs from Lattice QCD, as well as work with is it the UK QCD
RBC.
the RBC collaboration, is that correct?
They're all together. Yeah.
And today he will talk about us to us about what we're made of apparently. So
Yes. Yeah. So thank
We
you.
made a part on the lattice.
Apparently, yes, we're made of partons, but not very much of lattice. I guess your cells come into a lattice. But okay, yes, what are we made up of? Is the idea. So I, at Jefferson Lab, I work right about there in the CBAF Center, which is never in any of the cool photos of JLab, always showing the detector instead. But so, there we go, good. So here are some typical people, my siblings, in-laws, and myself walking around New York one time in 2019. And so if we want to try to understand who we are and what we're made up of, which is something people have been doing for hundreds of years, we understand that as we start to zoom in and look at people, we understand that they're made up of tissues and organs and cells. And then the cells are made up of all these organelles and chemicals which appear down. And chemicals, of course, are made up of atoms. And the subatomic particles, which we are all interested in, are become quite complicated when we begin looking into the nucleon and the nucleus, because our understanding of the theory is a little limited in our ability to actually practically apply the theory to understand what are these subatomic particles really made up of. So if we wish to describe what nucleus or nuclei look like in terms of QCD itself, we want to try to come up with a parameterization of how do we distribute our particles within the hadron itself. So you can imagine we have some proton moving in an accelerator quite fast, so it's become pancaked in the direction of motion. And this gives us two positions and three momenta you can imagine describing this particle as. You have the idea of how far away from the center is the parton that you're actually interacting with. Where is it moving within the plane of this pancake? And then how much is actually moving with the proton or whatever hadron itself. So you can imagine as our particle is moving as a cloud, the simplest object that we will want to be studying is this parton distribution function, which is just trying to understand this one-dimensional structure that if I interact with a particle that was part of the hadron, how much of its momenta in the direction of motion did it carry? And so this x is the momentum fraction in this plus direction. So in the last few years, the Lattice QCD efforts of trying to understand these things have really matured in the ability to calculate this parton distribution. And they've even begun doing some proof of concept and really trying to get into the weeds of calculating these more three-dimensional distributions, which is also what's going on in the experimental communities too at the same time. For decades, the PDFs have been analyzed from global experimental analysis, and really now we're starting to get into TMD structure, and there are some hopes of trying to pull out GPDs from experiments at Compass and at JLab, and of course, eventually the EIC. And so, how do we actually try to understand this structure from experiment? Deep and elastic scattering is the bread and butter of what happens at Jefferson Lab, and of course, SLAC was one of the first places that this sort of experiment occurred. And so if you want to understand what something is made up of as particle physicists, we throw something at it really hard and see what comes out. And so in this case, we are going to be sending electrons going into a proton with a very high virtuality here, which is what makes it deeply inelastic scattering. And we're attempting to see where does our electron come out. And in doing so, and seeing also what other particles may come out, we'll have access to these various features. And the nice thing about deep inelastic scattering is that it is one of these processes that have the so-called QCD factorization relationships that allow this picture to work. So what factorization is really describing this whole hadronic interaction, the electron interacting with the proton as a whole, in a way which is sort of very intuitive in quantum mechanics. When we're doing a quantum mechanical process, you say, from my initial point to my endpoint, I want to take all possible ways I could have gotten there. If there are multiple things for me to interact with, I want to interact with all of them with their appropriate weights. And so that's what the sum and integral are doing, is saying our total hadron is made up of smaller particles, which have some flavor index. So I could be the up quarks, the down quarks, the gluons, and so on. And then they also will have some part of the momenta in total. So the factorization relationship is saying, in order to get the total, you got to sum and integrate over all of the partons' individual cross sections with how how many of those partons existed within the hadron. So the PDF gets this nice probabilistic number density interpretation when you work it in this way. QCD eventually breaks down that literal number density interpretation, but this formula still works. So you can sort of think about it like if it is a probability distribution in this manner. And so this sort of relationship is something that we'll see also in the lattice calculations, is that we'll have some lattice observables, which will be related to convolutions over some partonic version of the lattice observable and the PDFs that we wish to obtain. And unfortunately, since nothing is perfect, this factorization is just an approximation. There are going to be some sort of power corrections, both in the experiment and in the lattice calculations, that we need to try to avoid and contain in order to have a well-controlled extraction of this function. So, yes?
So is there any already data confirmed this equal sign is good enough in some correction, with some later correction?
Yeah, absolutely. When you're, if you imagine lambda QCD over Q squared, when you start having Q squareds of 10G V squared, 20G V squared, you're in a pretty well suppressed regime, and it has been shown to work through these global fit analyses.
Oh.
So what happens is, as I was saying, you know, this partonic thing is an interpolation between our parton cross section and the our full hadronic one. And so by using many different kinds of experimental observables, people have been able to extract the common PDFs, because the same DIS that happened at SLAC, the same DIS at JLab with different kinematics, the Drell-Yan experiments that go on at CERN and other places, all of these have the same universal parton distribution that go into these sort of convolutions in these factorization relationships. And so if you try to study all of these simultaneously and you see some of them get very bad chi-squareds, maybe that low Q squared ones really do, that's where you start to say, yes, this is where that breaks down. And that's where this approximation is just poor.
Also, I mean, I guess that in practice, in many cases, the F2, the big F, the one that you are not determining, is approximated in perturbation theory.
Oh, yes, absolutely.
So then there are also log of lambda over Q corrections.
Yes, and those need to be treated in some manner. You can resum some of them, and I'll show some talks about that. In the lattice calculation, we're actually going to try to do a non-perturbative estimate of what that function is, which is going to be quite interesting. And I'll get to that too.
Your first one is not color neutral.
What? Did I not add the right number of colors in each of them? Yeah. Not to scale. They're partons you can't see or
But it's
whatever.
just still between color neutral.
Yeah, it should be, sure. I just threw in dots. This is about as artistic as I get when I'm making things. Yeah. Okay, so I mentioned the global fits. This is what they look like. So for the case of the unpolarized distributions, which is if you imagine your particle is moving and you want to take the average of the ones whose spins are aligned and anti-aligned with your particle, you don't care about their spins. These are very well understood experimentally. These are the ones that DIS, just if you just have a target and you shoot your thing at, you're going to be sensitive to. And these, you see these particularly big spikes in the large X region. These are the valence distributions, the things that, you know, the big one is the up quark and the little one is the down quark, because there are twice as many up quarks and down quarks in the valence sector. And then you see over here, these ones that begin diverging at low X are the C distributions, the anti-quarks, the charm, the strange, and this pink one is the gluon. The gluon, you might notice, is quite different in some of these as you start to get to the low X regime, because in these analyses, there's some cutoff of where the experimental data exists, and it is forced to extrapolate into that region. So trying to understand the gluon at low X is one big goal of the experimental programs, particularly going on at the
All this three at the same scale?
Yeah, what's the difference?
all three of these are the same scale. These are just three different collaborations. MSHT, this is who's in the middle, JAM's in the middle, this is in PDF.
So
So
they're
they-
all supposed to agree.
They differ in methodology and so on, but they are supposed to be measuring the same thing. So the differences between them, for example, are potentially model biases, for example. These groups use a particular fixed functional form. This group uses a neural network to parameterize their things. They also make different choices in how to estimate the error bars, what cuts to take on experimental data, these sort of fine-tuning things at the end of the day. But as you say, they are supposed to all be in agreement. So when you see these slight differences in the gluon distribution, that's a sign of potentially model biases or some extrapolation biases, things that need to be controlled.
That's not small differences.
No, no, absolutely. And I'll show you on the next slide.
When not Q score
Yeah. So this is the EIC white paper over here. Here is 10 to the minus 3. So let me pull back over here. Here's 10 to the minus 3. So this is where they're really disagreeing. The EIC is going to be filling in experimental data in this region, which currently just doesn't exist. So yes, it's a large change, but that's because we don't really know what's happening. And so that's where the EIC, for example, is trying to push down to this low X regime and trying to really understand that part.
Can you play?
Yes, but let me say the other part is JLab is doing the opposite. They're trying to push up to the high X. There's also an upper cutoff that also needs to be studied. And so if you imagine the very, very high X, which you can't see on this log scale, also has some errors that need to be studied. Well, this same sort of regime.
What is low X kinematically?
Low X, so maybe I have the other slide. X Bjorken is related to Q squared over P dot Q. So low X, you can reach lower X's by having lower Q squareds, Q being this virtuality of the photon. But if you go to the low Q squared, you're risking pushing up into this regime. So if you saw in the kinematical table, there are triangles and lines of where we find appropriate cuts.
So are you saying that EIC adds on for the unpolarized on top of Hera? I thought Hera has had much higher energies and therefore it should have a much bigger coverage. I'm surprised.
I believe it's supposed to add on, particularly going into the lower X region on top of Hera. Unfortunately, Hera is not plotted on these. Here we have Compass data and Hermes data and JLab all A data. But I'm not entirely sure where the Hera falls into this. But the purpose is to really scan much more of this space.
But Hera will be smaller X. So I still have a question. So these three groups use the same set of data or use a different set of data?
Largely the same. I believe there might be some differences in cuts of what Q squared do you accept, what Q squared is too low. But these are, I don't think, major differences between. There are, bulk of the data will be identical.
It's surprised because I know you didn't pro CTAC. CTAC maybe have different behavior.
Yeah, I just grabbed the latest ones here of, I don't know, the ones since 2021 on. I don't think CTAC has had one since then. So yeah, yes, there is a CTAC analysis too from 2018, I believe is the last one I remember.
I think CTAC is very close to GM, I think. And there has been some debate, for example, if you really plot the ground speed very small X, both the left one and the right one will go to negative. So there has been debate why Partons speed actually going to negative. I think CTAC doesn't go to negative. I mean, CTAC also initial scale is higher, I think.
I believe if you were to ask any of them really what's going on down here, they'll say not to trust what you see in the curves either, because they really understand that this is an extrapolation to these low regions.
Also,
No. Wait a second. The debate is about why Partons could be negative. Because you are talking about the fixed order calculation. I believe that all this next leading were Parton distributions. So
yes, I believe so.
In terms of fixed order calculation, you could have a negative Parton distribution because it's coming from renormalization and so on.
Yes, it normalizes series, they could be negative.
So in a sense, you can plot X down to 10 to the minus 4 or even smaller because that's the kinematic that you actually have some data there.
Well, you can plot it as like each of these are functional forms, right? So you can extrapolate that functional form as far down as you want.
No, it's not extrapolate. Some of it really have data there.
Some, yes, but there is less and less data as you get to smaller and smaller X.
These will all be
Also,
solved with letters.
Also,
Well, unfortunately, low X is where we cannot solve, unfortunately. We are in the high X regime, which is also very needed.
Also, I think that there is the issue of he was saying that this is a fixed order computation. So even if you take one people, only the NMPDF collaboration, they have the determination to NLO, and probably in the low X region, they differ by themselves. So this is one particular plot, but I am sure that the real uncertainty that they quote at low X is much larger than this plot, simply because the difference between NLO and NLO is probably large there.
Which scale is this plot?
Yeah, if I have to remember, it's 2 Jeff. I wish I put it on the plot, but I'm pretty sure it's a pretty low scale.
Strange data is pretty poor. I mean,
Yeah.
so that's the fit of strange is a problem.
Stupid question. Remind me, why is it that the anti up and down is bigger than the valence up and down at small x? I would expect that if you create, I mean, how do you define a valence up versus like an up?
So the valence up is up minus anti-up, because then you're assuming that the anti-up is the same as the C. And then the reason that you start to go up is because the singlet distributions are mixing with the gluon distributions. And what you might be able to see here is the gluon distributions here are divided by a factor of 10. So the gluon distribution is huge. And so that will start generating C quarks in low X region, where the gluons are blown up.
Okay. Sounds good. Thanks.
Okay. So yes, there is, as you say, data pushing down here. They're trying to extend it, but if we wish to really, these Q squareds are not very large. So if you wish to push to lots of data, many Q squareds, and getting a good systematic analysis, we need new experiments, and that's where they're going in this direction. All right. So parton distributions have a field theoretic definition. It's not just some function we tease out of these experimental datas. There is a real thing you can go and do a path integral, at least imagine you can go do a path integral and evaluate it. And so here I'm going to describe it in terms of first starting with the matrix element itself, which I'm going to call the Yaffe time distribution following Brown and company, which if you remove the Lorentz structure that comes in front of these things, when you do a Lorentz decomposition, you see that it's going to be in terms of just this new parameter called the Yaffe time, which is the dot product between a momenta and the separation between our fields here, who are trying to understand the parton distribution. So for the quark parton distribution, we have a bilinear here, but it's not like a normal vector current bilinear. This is the quark field and antiquark fields are at different locations, particularly separated by a light-like separation. Yeah. And similarly for the gluons, we have field strength tensors separated in the same manner, with a particular choice of these indices that go into it. Now, the nice thing about using this Yaffe time here, it's a dimensionless number, which dimensionless numbers are a lot easier to work with, but it's also the Fourier conjugate of this x momentum fraction, which gives us this nice relationship. Usually the PDF is defined in the inverse this integral, and that's how it's defined, the Fourier transform of this matrix element. Now, unfortunately, this light-like separation is going to become a problem for us on the lattice when we get to it, which is for now, the first feature you need to know about Lattice QCD is done in a Euclidean spacetime for computational reasons. If you try to do it in a Minkowski space, there's a sign problem and you have exponentially growing costs that make it completely impossible to do. So instead, we are forced to use Euclidean space. Now, as I said, the separations that we require are light cone. We want things with z squared equals 0. So in a Minkowski space, you imagine that you're doing an integral to undo that Fourier transform by integrating along this light cone direction. In Euclidean space, there is no light cone direction. There is only a single point that has z squared equals 0, and this isn't the non-local object we really want to understand. And so the change that happened about a decade ago is when Jainamji proposed to start embrace the Euclidean space, start using these space-like separations instead. And that we can then find from the objects that you have with these space-like separations that a similar factorization as the experimental cross-sections had will appear. And this is going to be one of the ways in which we're going to try to combine our experimental and lattice analyses is that the same formulas are appearing here. We can do the same sort of global fitting methodology, but with all of the data together. So besides these approaches, there are actually very many approaches on the lattice that people have been doing to try to understand parton structures and trying to get the PDF out. This was probably K-Fay proposing that we should calculate this hadronic tensor thing. Yeah.
Sorry, what does space-like separation mean in Euclidean?
Well, all separations are space-like in Euclidean. So, yeah, exactly. But actually, that's a very good point because there's another catch which Raoul and company figured out, which is that if you wish to do the Wick rotation from Euclidean space to Minkowski space, you don't want just space-like, you want literally spatial. So not just that, the T separation is smaller than the spatial separation, but literally equal time correlates. So that's a good question because we want space-like, but we want literally spatial equal time correlators in this case.
Or another way of saying that is that whatever spatial operator you consider when you Wick rotate, you're going to obtain the result that an observer would see for which the operator is a real operator in Hilbert space, so it's at the same time, right?
How do I want to put it? The issue, as I understand it, is if you want to do a Wick rotation from Euclidean space to Minkowski space. So when you're doing lattice QCD, you keep times very explicit, so that if you want to be able to relate things like energies, for example, if you're analyzing 2-point functions, you're keeping the time very explicit so that you see there's an exponential decay in Euclidean space as opposed to a phase which would occur in Minkowski space. And by knowing what your time dependence is, you tease out what this energy is. Similarly, when you're trying to analyze matrix elements, you put the operator whose matrix element you want at a very specific time. That's an important piece here because if you did a spatial one but still had a time separation, you're having fields that transition along multiple times. And this is what hurts the Wick rotation in the LSE formulas, if I remember how your paper worked long ago, whatever it was. So yeah, keeping things in exact times is very important for lattice QCD in order to relate to Minkowski space. All right. So okay, many things you could do, and they fall into two real classes of observables. The one which Zhengdong proposed was these Wilson line observables, which really look like your PDF definition. And then there are other ones which are related to matrix elements of two currents. And depending on how you treat those two currents are what really distinguish all of these various approaches and which currents you're using and so on.
I mean, except the hadronic tensor, right? Like that one, you guys are proposing to do it at different times, right? Everything else is at equal time.
Yes.
So that was very, very different.
These are at, yes, these will not be at the same time in there. So that is probably the most unique out of all of these. The rest of these are all equal time as well.
Yeah, then you would do the structure functions instead of PDFs.
Mm-hmm. So yes, that is the big difference there. And I believe the Hope method, the difference is, this quark is quite heavy. These two, I believe the authors have now decided are exactly the same. You're doing just the space-like separation. And this one involves doing a Fourier transform of this separation and taking some particular limits.
I mean, the good lattice cross-sections and hadronic tensors are closer to each other, right? They stuff like, I mean, it's like
yes, and you're talking about equal time versus not equal time. Yeah, yeah. So they are quite close, and they would be using the same sort of currents there.
But I saw it. So his proposal is almost like an experiment, right? So
Yeah, exactly. You have x and q squared.
Yeah.
Both x and q squared.
But the
So
difference is
does that have this problem when you?
yeah, it does. So it's because it's not equal time, then it's not like experiment. Because
Oh, it's not like
we're in a Euclidean finite volume, right? So then like that
Yeah.
has its own kind of
The
drivers.
inverse problem back to you.
It has a different
Yes.
kind of set of problems than everything else that is there.
But this inverse problem, you particularly are treating it in Euclidean space. So you're saying instead of having a phase moving in time, which is what you would have a Fourier transform with your time direction, instead it's the Laplace transform, which is the exponential decay in Euclidean space. So by keeping the times explicit and analyzing the time dependence, you're able to relate to the Minkowski space one in this method. So that's another example here. Keeping the times explicit and well understood is important for getting to Minkowski space. All right. So I'm going to focus on these Wilson line matrix element calculations, where what we're going to be doing is we're going to be calculating this matrix element up here, which is some same looking thing as we had for the PDF definition, except for the two changes are we relax the z squared equals 0. We want to really be space-like, and we don't immediately want to say what we're doing with here. In the PDF definition, this alpha was plus. But if you consider it generally, you'll see that there are two terms that can appear in the Lorentz decomposition, and this is the one that appears in the actual calculation of the PDF itself. So this is the one we want to get at. Now, in the proposal of large momentum effective theory, you first calculate from it some integral in order to get the so-called quasi-PDF. And then that quasi-PDF has this factorization relationship, just like the experimental cross-sections, that there is some data you have, and it is a convolution of the PDF and some power corrections. Now, the method that we're going to be applying, which is related to it, coming from the same object, and it's approaching the same light cone limit in a different manner, we will still have the same sort of relationships, be it to the PDF or to the Yoffie time distribution that you want to be considered, and to a different set of sort of power corrections that come out. So the primary difference here being, which limits are you taking? There is a P and there is a Z. You make one large, that's limit. You make the Z small, that's the short distance version. And so this is all sort of familiar if we compare the two variables, P and Z, to what you have in the structure functions. So structure functions have an intrinsic scale Q squared. And this is the one that is governing your power corrections. And this is the one that's going to appear in your perturbative calculation with the big logs. And so this is the one, you want to keep it away from lambda QCD, for example. And if you really trust your calculation, you could just do this once, choose one scale, and then you believe you can do all your formula correctly and get a final result. Now, global analyses have many ranges of Q squared, so they can test these assumptions. And this is why getting more data at low x from the EIC is important for understanding low x, so that we have more Q squareds to make sure that we're really in a place where our power expansions are under control. Now, on the other hand, we have the x Bjorken in the structure functions, which is really our dynamical variable. By scanning x Bjorken, you're learning about the x distribution in different ranges. And similar for the quasi-PDF and pseudo-PDF, this is where the separation of momenta come in. Or you could have used the Yoffie time, as I was saying before. And so this is these parameters you want to scan as much as you can. So you want to do your lattice calculation capable of having as many values of whichever one you want to be scanning around so that you can undo these integral relationships as accurately as possible. So here we, yes, yeah.
Do you know why it's called Yoffie time?
Yes, yes. Well, okay, here, P.Z. So in the analysis of DIS, Yoffie proposed that this relevant time scale of the interaction is related to, or mass times time, and this is what produced the Yoffie time. So if you imagine the kinematics here of the rest frame, something interacting with a proton at rest, m times t, and that's why it's a time variable, is essentially the idea. So this Yoffie time is sort of telling you the time scale the interaction was occurring in units of the inverse mass. So that's just one interpretation of the thing. But for us, we just care about the Lorentz invariant combination, not the particular frame relevant for DIS, right? DIS is the proton just kind of sitting there at the target and the electron comes in. And that's why you get m times t.
I think I have to ask my standard question.
Please.
So my standard, at the light cone, you could have a singularity, right? You know this from correlation functions. You come from the space-like region, it jumps, and there's this continuity at individual time-like region. So now you sit on the light cone. On which side of the light cone are you sitting? Now, I'm getting confused. I'm always told it's the space-like side of the light cone, but now with the Yoffie time, now all of a sudden it's a time difference, so it's a time-like. What is it?
Well, this will be, P.Z will be a space-like combination. So my Yoffie times will be negative. I'm still calling it Yoffie time for the same reason I call proper time.
Space like this.
Yes, absolutely, absolutely.
And then I can believe that is okay.
Yes, yes, that is important. Yeah, indeed. You know, we call it, and we learn special relativity. You talk about proper time, but you could do a negative, positive proper time.
Yeah,
still
okay,
proper time,
okay,
right?
right.
So yes, it is space-like, absolutely.
Like light cone minus epsilon. Right?
Yep, absolutely, yes. So yeah, and when it's tricky, you got to remember when you're actually trying to figure out what this number is from your calculation that there's an extra minus sign from the lattice. You'll realize you get negative numbers in your imaginary component. All right, Lattice QCD. We have big computers. It's the most important part of Lattice QCD. They're cool. They're fastest computers in the world that we're running these things on. And so the reason that we must use Lattice QCD for these sort of analyses is that the definition or the actual observable we're trying to get, this parton distribution function, is really intrinsically non-perturbative. Our ability to actually understand these hadronic properties from QCD just fails. And so the numerical lattice field theory is nice in that it can work at any coupling. It can also work at any quark mass, which quark masses, of course, make perturbative calculations quite difficult. And all of the approximations that are made to do so are improvable. That if we work harder and they build us bigger computers, we will get better answers in some limit. But of course, there's a lot of approximations that I'm talking about here. Which those, you will see, there we go. Some of the most important ones here are, for example, our regulators. We have our finite lattice spacing, which is our UV regulator, which can actually be a huge problem in many observables. We have our finite physical volume, which for the hadronic calculations we're doing is a problem, but for hat spec it's actually useful. And then we have other things that go on which are steadily improving. Our ability to understand these Wick rotations from Euclidean space to Minkowski space was questionable at first for these PDFs, but after Raoul and company helped explain some of these things, we now understand these. We can now do calculations quite cheaply at physical pi masses, but still for historical reasons we keep doing runs at heavier pion masses because A, we have a bunch of configurations, they're a little cheaper to do calculations on. And then there is signal to noise problems, particularly if you're dealing with disconnected diagrams, which are required for isoscalar matrix elements. You're going to have these large issues with signal to noise. The thing will be orders of magnitude more noisy than the isovector combination. So a lot of the results I'll be showing real quick are going to be from this isovector setting. So okay. In practice, how does Lattice QCD work? If we want to obtain matrix elements, Lattice QCD begins when you're doing hadronic stuff with the calculation of correlators from your supercomputer, which are vacuum expectation values of operators who are time separated, with your times very specifically labeled, because the time dependence will be described by the series of exponentials. And you really want to pull your operators apart so that the only exponentials that are governing are your ground states, the ones that are your nucleon or your pion or whichever system is really interesting to us. And so this step of going from correlators to matrix elements is pretty standard. The idea is that as you pull out to the long times, you're eventually plateauing your very noisy data, but your noise is exploding. And so if you can try to model some of the low time excited state effects, you can get a nice plateau. And then that plateau translates to your matrix elements here. So this is the pseudo distribution of the gluon. It's calculated by Tanjeeb Khan as part of his PhD work. And so this is just the first step. Now we actually want to go from our matrix elements to our distributions themselves. And this is where this inverse problem comes in for our case. So if you remember, we have our matrix element equals an integral. We have a discrete, a finite number of data points here, but we want to understand a continuous function, an infinite amount of information. This is clearly an ill-posed problem to go from finite information to infinite. So in many of the phenomenological analyses, here are some of the ones shown for the gluon, they will choose a particular functional form. And in this case, we chose this one, which is just the most basic idea of what a PDF is. It goes to 0 at 1, and it does something at low x that flops around. And we get this nice blue band, which is in the ballpark of what the experimental analyses are. This, frankly, with this sort of noisy data and the results that we got, I was surprised how well this worked. This is one lattice spacing. This is a very heavy pion mass. This is one volume. And we're still getting right in the right ballpark here. So this was quite nice as a proof of concept. We can get these gluon distributions, which are particularly noisy for us. Now, in the quark sector, there's been a lot of work over the last few years. And
So,
here,
sorry, what was the pion mass for you?
350 MeV.
Oh, okay.
So it's quite heavy.
And it still looks pretty.
It still looks pretty good. We're thinking that it's possible the gluon distributions are slightly less sensitive to pion mass than quark distributions, for example. We're not entirely sure on this, so we're going to be pushing it down, of course. But so far, the gluon calculations are some of the most noisy for us, so that's not the first things we're trying. That's we're pushing these downwards.
So, go ahead.
Sorry, I remember last time you talked about you are planning to do the machine learning phase.
Yes, and I have some backup slides and some machine learning stuff too.
Okay.
But yeah, so NMPDF is one of the experimental results, and so this big pink band comes from using a neural network to parameterize the function, as opposed to something like this. And so we've worked with NMPDF as well, trying to do these as well as other Bayesian-based approaches to reconstruction, which give you similar results to what you see from the fixed functional form. Though we're working on trying to study how, as you change these different methods, you combine neural networks and other approaches and see how you get the most reliable error bars. Because this will have some model bias because we chose this function. We chose a different function, you get a slightly different curve. And so this is one of the directions we're trying to push. Though the machine learning stuff that I might show is for a different application. That's to the evolution stuff if we get to it.
Okay.
So I followed the lattice attempts, I should say, to get the shear viscosity from the lattice, right? For that you have to do an analytic continuation, but it's also one of these inverse problems.
Mhm.
In this case, I mean, whatever you put in, you got out, right? So there's one. So why is yours easier? Why do you believe that? Is there an argument why this should work better than this other stuff?
Yeah, the limiting factor for us is this range in Yaffe time. So the wider we can push this range, the more reliable our extraction is. And we've done a few model studies of seeing how well, if we put in a known function and we try to make mock data and see if we try to reconstruct that known function, how well do we do? If you have a range from 10 to 0, which is not shown here, that's more realistic for our core calculations, you can trust about up to 0.2. And then anything below that is, you're probably going to have some systematic biases.
And your error bars don't hurt you, because in this case, in the analytic continuation, there I heard a talk, you could have as many points on the Euclidean side as possible, but when you deviate a little bit from the true solution, your prediction for the shear viscosity goes wherever it wants, right? So you're not worried, you're not affected by the size of your error bars. I mean, having many points is good, but if you have uncertainties in the points.
Certainly, yes, and the size of the errors is relevant.
This is because you do some ansatz for the correlation or for whatever for your.
Well, in this one, yes, and that does constrain things much more than if we were to use some of these more Bayesian or machine learning techniques. We would get larger errors if we have this sort of.
So why should the ansatz be correct?
I would say there's no great reason.
No,
this is the simplest.
What I can believe what is put in.
So I think that there is.
Okay, go ahead.
I think that there is a bit of a difference also in the C function. That
Yeah,
is the convolution of the two functions.
Yeah.
So I think that I mean, if this function makes your integral peak in the region where your data is relatively precise, then okay, you should blow your uncertainties at large x, but there is a region that you can certainly guess this thing.
So this C function is a cosine, right?
Exactly.
So this doing these inverse Fourier transforms is well studied in the field of signal processing. And so they understand how you can estimate from even just looking at these things, what are the frequencies you can trust, i.e. what are the ranges of X you can trust.
But if you put there a crazy function, then
it will be.
Gosh, right? I mean, I mean,
This is much better than the exponential.
Yeah, exponentials are hard.
And the other thing is that if you have a degree of freedom and matches up with the data, then you just inverse the matrix. Then that's it. Here, if I don't know about the positive PDF, quasi-PDF, you can do the Fourier transform. You have all the momentum fraction you have many data, and that will be a lot easier.
What data? Experimental data or lattice data?
The lattice data, but when you transform the Fourier transform, you have all the X. So that's the large number of that you can do the fitting. Whereas if you do other cases where, as I said, if you wanted to have a small data set and you want a whole distribution of that, that's very rare. That's a huge inverse problem. In other words, the degree of it do not match.
So to some extent, the uncertainty was a drastic underestimate for large X and small X radiated both. But I just want to comment on your question. So the ground description goes like that. There's an educated guess. It's a power counting postcode from power counting analysis and large X. And the small X we know also there's a rigid behavior for the ground description. Right? I mean, if you don't know this, I don't think Joe will fit with this function, right? So you will fit with something totally different.
So if I let a neural network, a totally stupid like myself neural network on this, which doesn't know anything, then you could get off. Whatever. Okay.
That's actually my question to him, because, but he didn't do this.
But yeah, so we.
But this kind of inverse problem is exactly the same as the one from the experimental determination.
Yes.
I mean, these people they have the left. The only difference between the lattice and the LHC is the left hand side. Here he's using lattice data, okay, And the experimentalists use the experimental data from LHC.
Exactly.
But the fact that you have to disentangle the
Okay.
convolution of the function is the
Okay,
same.
okay, okay,
They
fair
have
enough, that's good information.
thousands of data, and they have, I would say, a dozen of parameters with some functional
Okay,
form.
fair enough, fair
And so
enough.
they can really fit it. It's not really an inverse problem, it's gonna fit it.
Well, there's always systematic issues with parameterization, so that's what we were talking about at the beginning of this talk, right?
Yeah, a different change function.
Of course, you
Yeah.
have to make some assumptions. This is clear.
Yes, and then you want to vary these things. Here we did, I'm showing you one, we did a couple more, which include modeling systematic errors, and they're giving us in the same ballpark, and I'm just showing you the simplest possible thing in the philosophy that the fewest parameters in your functional form is probably going to be best and less biasing yourself.
If they really measure the same stuff experimentally, why don't I compare this before I go through
They're
the
not,
structure?
they're not.
It's not, it's a
The
integral
C
of the
function
same
is
form.
different. The C
Here, I'm gonna
function-
jump ahead to something.
The C
All right.
function is different,
Yeah.
the left-hand side is
Sorry for
different.
being so
Yeah.
stupid.
No, it's fine. This is what experimental gets. They have some differential cross-section convoluted with their PDF, common thing. We have some matrix element convoluted with a different thing, but to the same PDF. So we'll have different power corrections, different systematic errors. There'll be different natures of the inverse problem, because like this integral is going to be different than this integral. And that'll actually be an advantage for us when we try to do combined analysis, that our integrals are slightly different from each other. So, get to this. Okay. Good. So many people calculate these things, and they're trying to scan the various systematic errors they have. And so this is the sort of work for the unpolarized quark distribution. This is the one which experiment knows really well, and we've been working and benchmarking with the experimental numbers to compare to. And so as you see here, for example, the group out of ANL, BNL, and I think maybe MSU, if I forgot to label them, as they change their momenta, increase their momenta, improve their power corrections, they're approaching something which looks more like the true PDF. And similarly down here for the group of ETMC doing their work, and we have our calculation here that Colin Eggerer did. And we're getting right in the same ballpark here.
Here's a challenge.
Yes.
I'm particularly interested in active X region, U bar minus D bar.
Yes.
Some violation is. Now, how well, we can see the first figure in that they're already different, right? How well can we, the status that we can control that in the U bar minus D bar in the next group?
You'll actually see here we have the valence. In our work, we have the valence, and we have the so this is Q minus Q bar, this is Q plus Q bar. A thing about the lattice matrix element, which I didn't describe, is that the real component matches to Q minus Q bar, and the imaginary component matches to Q plus Q bar. So what we have always done is we analyze real and imaginary components separately. So when we go and look at Q minus Q bar, or then when we start asking about the anti-quark distribution by adding or subtracting these, we see signs that are consistent with the sign that comes out of the phenomenological analyses. The group of ETMC and these group ANL and BNL, they fit the complex number simultaneously for the positive and negative region. So this means that they have a harder inverse problem, in my opinion, and that could lead to systematic biases in both of these regions. So I would say if you split it up in this manner, you're going to get the right sign, and you're not going to see these sort of inconsistencies.
Do you see something reasonable, the numbers?
Yes, if we do.
That would be interesting.
For here is the anti-quark helicity distribution, which we calculated, and it's right along the same areas where the experimentals are, which is 0, but it's fine. And then over here we have the polarized. So even in the unpolarized case, we are getting in the right ballpark in this case. So we're still not in all of the full systematics in this case, but yeah. Wait, you want me to go back a slide? What do you mean?
Yeah.
Yeah.
The power corrections on the lower left plot are clearly non-monotonic. That was rather troubling.
I agree entirely.
Blue, it goes blue.
Yeah,
green,
blue, green, red, and then you look up here, the same ones, it goes blue, orange, green. It's not the same. I am not sure what generates this difference between their analyses.
But that would, to me, suggest you're clearly not in a regime where the power corrections are under control.
Yeah, for these Lamette calculations, I would agree. You have to do a lot of work, even to get the perturbative in to look like it's under control with things like threshold resummations and even resumming renormalons and some things that I don't fully understand on that end. So yes, how well do you compare and converge here is an important question. And this goes to the point of trying to study multiple scales, which I mentioned. In our analysis, we have about 6 scales that we are using together, and they are being combined to get one curve. So I can't show you what the deviations between them. And unfortunately, I didn't include the right plot. There's another plot of this where our systematic error corrections are plotted. And you see the things that look like our power corrections are pretty small compared to our actual final result. So we attempt to model away these differences in our analysis. The people who have done Lamette so far do not. So you just see these deviations and they expect the deviation to be a sign of their systematic errors, and those get included in a final error budget.
So these P's are the P's that enter in the power corrections.
Yes, exactly,
So
yeah.
lambda over P in some of these plots is in fact larger than 1.
Well, yeah, they're showing the low P's here to be showing you the limit of very low, but they really believe these 1 over 1 GeV, they really want to push to 2 GeV in some of their other calculations to really be trustworthy. And so ETMC has been much more conservative about the largest momenta they ever show. They rarely go over 1.5 GeV. Some other groups will go up to 2, including us, but those really become much noisier. There's an exponential growth in the signal to to the noise to signal. Noise blows up as you go to large momenta for. So it's really
bad. The problem of going to larger momenta is that these momenta in lattice units has to be large.
Absolutely, this is
this is probably
approaching
not
1.
a single lattice spacing.
Yes.
It should be around 2 inverse Jeff, so that puts a big. I mean, it's a
absolutely, yeah.
There are multiple scales there, and it's difficult to fit them. I mean, it's amazing that this thing works.
Yes, if we're not controlling
with all the compromises that one has to do, I mean, it's amazing that this thing works.
I entirely agree. And as people have started to improve things like understanding what are ways to take continuum limits, we've seen improvement because these effects are very important. So for sure, there's a lot of knobs here that are, at face value, do not look under control, and you need to carefully study each of them to make sure they are under control. It gets even worse when you start to get into the GPD case as well, where things like lattice spacing errors will start to become much more prevalent.
So what is the maximum momentum in lattice units, for example, for 2 GeV?
It depends on your volume 2, or whatever, right?
Yeah.
So on a 32 box, let's say, we only ever go up to about 6, which is more than A times P is more than 1. This is bad.
The magnitude of 6 or 6
yeah.
in each
2 pi times, only one direction has momentum. Only the Z direction.
So it is the magnitude of P2.
Yeah, the magnitude of P, 2 pi over L times 6 or something like that. Maybe this is 2 pi over 3. Yeah, 1, 2, 3. These increase in So that's why they're being more conservative here, trying to keep that down, as well as the signal to noise problems. So yes, this is a huge problem going into these calculations. One of the things that I would say is an advantage of the pseudo-PDF method is allowing the low momenta data, but the catch is that it requires short separations. So the separations we're using here are 2 lattice units, 3 lattice units, and we found in our modeling that you have to model these A over Z sort of corrections in order to get a consistent answer. But when you do so, you get a nice consistent answer over a range of many scales, which is giving us some belief that we know what we're doing, that we're somehow approaching a actually controlled calculation.
Would the distillation helps you getting up to a higher momentum?
Yes, distillation helps our signal a lot, it seems, for the same amount of work that is just really cleaning up what's happening. Because if you imagine the other approaches, which are point sources, they're going to have more translation and variance, I guess, breaking of translational symmetry. But in distillation is using a wall source in a way. The eigenvectors span the entire volume. So when you do a momentum projection there, you're getting a lot better improvement in your signal.
Why are you guys only considering momentum on the z-axis again?
It's a good question. The reason is simplicity for the biggest one. If you imagine, we want to make a Wilson line that goes parallel to our momentum because we want to have P dot Z is the relevant parameter. So if you want to have your Wilson line off, you have to suddenly start doing staircase sort of shapes in order to go in non-trivial directions. So that motivated everyone to do Wilson lines just along the axis of one of the lattice directions. So then one could rotate the momenta away in order to have momenta not parallel, and you'd still have a Yaffe time of some fixed number. But this would only increase the noise compared to having the aligned one with the same magnitude.
Oh yeah, being stupid. Can I take the dot product of two vectors that are not pointing along the
Yeah.
same direction?
No, but like if I calculate 0, 1, 2 and 0, 0, 2, these would have the same Yaffe time, but this would have more noise. So why would I calculate that instead of this?
Because it would kill the power corrections of Lamette.
The power corrections of Lamette also only matter about the direction of your Wilson line.
Ah, okay, so you have.
Which is a
no-
catch, yeah.
Ah, okay.
Yeah.
So it's always P dot C, or P dot.
Yeah, the power corrections come from the same thing, which is that you would say your matrix element is equal to your convolution of your true thing, this C convoluted with that, plus Z squared times something. This is the Lorentz invariant breakdown. And then when we want to do Lamette, you would say, okay, in the particular frames that Lamette is being done, PZ squared, or whatever is relevant, is equal to nu squared, or Z squared equals over PZ squared. So you see these power corrections come from the same thing, and it's really long separations are what drives the power corrections. So when you push the large momenta, and you keep Yaffe time large, you're still doing small separations, and therefore the large momenta is giving you small power corrections. So this is one issue that I have, is that the power corrections have the same source, and it's just how am I manipulating these limits give me the differences between the power corrections in Lamette and the power corrections that we have. Okay. So where was I? Here is, I was just going to flash these results. Here is the Helisty distribution, polarized. So you imagine the quarks that are in the direction of motion minus the ones against the direction of motion. This is also quite working well. People have done the transversity, so perpendicular direction of motion minus the other perpendicular direction of motion. We have many calculations going on here, and this is one where we really start to see that the lattice data is coming to be quite competitive to the phenomenological abstractions. Here, if you look over here in our analysis, which was big work done by Nikhil Karthik, our extraction here, which maybe is still got some model bias and the errors need to be fluffed a little bit, are smaller than what is coming out of these latest jam analyses. So we're really starting to reach the point where our precision is starting to become relevant. And that means we really need to make sure that we understand what we're doing so that we can start making useful predictions for people in this manner.
Is that non-physical quark again?
Yeah.
Yes, yeah, absolutely. Yeah, and I believe all of these are.
Uncertainty does not include estimated extrapolation of physical
Yes, it is statistical and model variance. We changed the models a bit in order to study that and used an AIC averaging in order to make an estimate. And that's the difference between the slight bands out here, if you can see the difference between the two, is from the model variance. So the model varying down here had an increase of the errors. As we changed the model, we got slightly different curves. Some of the curves peaked right here, some of the curves peaked right there. And so that gave us different answers. And this expanded our errors.
So I think I've heard you say this before, but I forgot. What is the reason for the uncertainty, the red band, like becoming smaller for that one point and then becoming larger again?
Right. This is a highly the relation between this curve and our data is a little complicated, right? It comes through this Fourier transform. And there are very precise degrees of freedom in our data, which come from the low Yaffe time, which are constraining the lowest moments of the distribution. So the integral of each of these curves is much more precisely determined than the curve itself. So as I said, there's some curve that peaks here, and there's some curve that peaks here. Those have almost exactly the same integral, even though they have quite a different low x behavior, where the peaks are somehow shifted by 0.1-ish or something, not necessarily a small amount. And so that makes proper error bar estimation itself a very difficult subject, both within the phenomenological analyses and within ours. This has been the last few years, CTEC and NNPDF have really been debating what is the proper way to say, what is my error bar? Do I do Monte Carlo resampling and see my spread of different data results? Or do I just take the Hessian about the minimum of where my fit goes? And which of these is correct? And so this is something that a lot of people are working on, including us, in trying to understand. So far in the analyses that I'm showing, we're really using a handful of functional forms and doing our best with that. But we want to be trying to improve this as we move on in the future. Just not quite there yet. But same with the phenomenological people. They have the same problems. How do you make a good error bar? It's important. All right, so we can make nice PDF fits. It's great. We're in the ballpark of experiment, but that's not necessarily the only thing we can do. but particularly since the unpolarized distributions, which are the ones that go into a lot of analyses outside this field, we are not competitive with. So our ability to look at them individually and directly from the lattice is maybe not the most interesting. So one direction we started looking at is trying to understand the evolution of parton distributions. So the PDF has a renormalization group equation here called the DGLAP equation, which says that its scale dependence comes through a convolution of the PDF with the so-called splitting functions, where these splitting functions come from understanding that your quark could be moving and then it radiates a gluon, and now your quark has a slightly smaller momentum fraction. And so how those alpha S effects come in and change the PDF itself. That's what DGLAP is describing. Now, in practice, when you're doing a phenomenological analysis, you'll have a PDF with an explicit functional form at some low scale, like the charm quark mass. And then that gets evolved all the way up to some larger scale by integrating this equation. And so you can imagine that there exists some convolution that takes you from mu naught to mu. And this is how you will then move you up to the high scales where your experimental data is and where you want to handle. Now, we're able to see a similar set of relationships for the pseudo-PDF. We remember our relationship and we say, well, our pseudo-PDF didn't know about the MS bar scale that appears in factorization. You can then turn this around and find what is the z-squared evolution of your matrix element and have a similar scaling here, which would take me from a z-naught to some different z-value. And it's these two integrated evolution functions, or step scaling functions as we're calling this, Lattice QCD has a similar idea. They're related to each other by some convolutions with these kernels and the inverse of this matching kernel. So what we want to try to do is try to understand this evolution of the pseudo-PDF. Now, if we wish to compare and we want to talk about some scales that exist in lattice QCD calculations, this is separations of 3 lattice spacings. This is the scale at separations of 2 lattice spacings. You should be pretty afraid of seeing 700 MeV, and I'm going to tell you I'm going to use perturbation theory. This is not in the well-controlled regime where we can calculate that thing correctly. But, well, we can still just do the calculation and see what we get. So if we imagine going from half this scale to twice this scale, we'll get one of these bands in the lower part of these bands for this spread in each of these. So we have the blue here is the leading log resummation of all those large logarithms, and orange is the next to leading log, and you get some curve that comes out. Now for the pseudo-PDF, we get something that looks quite similar when we calculate it in perturbation theory. Generally, it's a little lower here, which I don't know if there's anything really meaningful to that, but it's another curve. And so these are the sort of convolutions that would be done to manipulate our data in order to get to do z-squareds. But why should we limit ourselves to perturbation theory? We have data at different z-squareds, and we can attempt to infer what the sigma function is from that data. And so in this way, we are non-perturbatively learning what our evolution function is. We're not going to have to rely on a perturbative calculation of splitting functions and hope that alpha S is going to be small enough that the series converges well. Instead, we can attempt to model our data in the slight z dependence as a function of Yaffe time, and what we end up getting is this gray band that comes out. And it's quite consistent with the NLL calculation that we had done before, maybe a slight variance in what the error bars here for this proof of concept analysis. But this is quite an interesting feature, that we can non-perturbatively study these things that usually are in the realm of perturbation theory. And as we're going to start moving on, we need to push this to finer lattices and to doing things like the correct pion mass so that we can try to improve what these extractions are. Particularly finer lattices will allow us to fill in some of the space in Yaffe time and get a more accurate reproduction of what this function is.
So what do you mean that requires assumption on leading twist terminals? Is because you are neglecting the 1 over p squared or q squared terms.
Yeah, exactly. When you derive what this is, you completely drop any power corrections into this. So that in itself is a systematic error that will come into this. And our way of hoping to study this is to use the universality of the DGLAP equation. This splitting function is the same splitting function for the pion PDF, for the nucleon PDF, for if I go and calculate a quark PDF somehow in some fixed gauge or whatever. You would have the same splitting function. So we intend to do this calculation again with a nucleon, with a pion, and with whatever else we can do. and study the z-squared dependencies and where they start to deviate from a universal behavior, that's where our power corrections are coming in to become a problem. So if we can scan this range of scales, here we just did one set of scales, but you imagine we do a lower scale and a lower scale, and eventually the pion and the nucleon will be different because the pion and nucleon structures of these power corrections are starting to come in.
Sorry, but maybe but at the same time they have different PDFs. So
Yes.
So can you extract everything at the same time? Or because in this game that you are playing here, you are relying on the PDF determination.
But no, we could do it. If we had pion and nucleon data, we could do a fit for the same thing simultaneously. The reason I hesitate is doing that doesn't allow us to check whether or not we're in the good regime. We might just get an answer and that's what it is.
But this is what I don't understand. The M function, the PDF would be different for both of them.
Absolutely. And
so
this
the data would be different, the sigma will be the same, the other function is the same, but then if you don't assume the function, you cannot.
So this is one data set. This is a different data set. So here you'll see some data appear in purple, and then here you have some data in green. These would be the two different scales. And we would calculate a different set of two different scales for the pion, which would be some different curve, and we would have two different data sets as well added into that.
Yeah, but where do you get, okay, sorry, we can discuss it. I don't understand, it's my problem. No. Okay,
well, first let me see if I can, good, okay. All right, and here we get to the global fitting part of this, where now we have this idea that we have the same PDF that we want to learn from all of these analyses. And because it's getting kind of late, I'm going to try to speed up. All right, so the fact that these convolutions are not identical is important here, is that the experiment is going to be limited into the range of X Bjorken that it can have, which is towards the very low end of the scale. And there's some upper region in the vicinity of 0.6 or 0.7 where they can't really have sensitivity. But as I argued earlier, the lattice data, on the other hand, is really sensitive up into the larger X region. So there's some overlap, but there's also some regions where we constrain things separately. And this means that adding them together can really improve the analyses more than any one could have individually. There's also the problem with analyzing Drolian experiments as you go to very large X, is that there are logarithms that diverge as X goes to 1, and these need to be resummed in some way, which is quite complicated and very sensitive to the nature of the integral that is the convolution for the PDF. But on the other hand, for the lattice, we have an integral over the full range, and we lack this sensitivity. And this became quite important for our analysis of the pion PDF, where we took in lattice data that we had generated and combined it with experimental data from Drolian and from the Sullivan process. And we were able to extract functions that are quite consistent with, or rather, in the simultaneous analysis, we're able to get things that agree quite well with our data. And here we have some systematics included in the deviation from our leading twist. It's a very small difference. So the higher order effects are things that we wish to exclude, not contributing well. And if we compare the results of the PDF that come from a lattice-only analysis or experiment-only analysis, or the combined is much better. So here is an observable which describes the large X behavior that Patrick Berry likes, called the effective beta. And you see our lattice result alone is huge. We don't really understand what this parameter is very well because we had a very limited range of Yaffe time. If you see this, I told you we needed to get up to Yaffe time of 10 to try to get to low X region. Here we're up to Yaffe time of 5 before our signals start getting too bad. But anyway, if we combine it with the experiment, we can see down here in the relative signal, relative error to signal, that we see reductions of the error bars of factors of 3 by combining in lattice data. Our lattice data did not have many systematics under control. We had to model some of them, but some of them we didn't, and we still see a huge improvement, and the data seem to be quite consistent. So as we add in more better lattice data, particularly for the pion sector, we hope to have a huge impact on these experimental analyses. The final one is this work on the gluon distribution. Yes?
And it's the same question for a third time.
Yes.
What's the pion thing?
Almost all of these are at 350.
I imagine I was just thinking along the same lines.
400 for this one.
So what does it make sense to combine experiment with 400 maybe?
To see if it worked. It's the reason why it makes sense. That is certainly a systematic we need to get under control, and it will change what this analysis is at the end of the day. But this was to show proof of concept. What sort of impact can lattice calculations have? And it turns out it's huge. Factors of 3 in your errors at the end is ridiculous.
Yeah,
But so
it's hard to, it's hard to make strong conclusions, right? You're comparing two different universes with different quark masses, and then you're like, forces them to be the same, and then saying like, oh, it happens to coincide and it reduces it can reduce the errors. It's hard for me to.
Yeah. Yeah, you're not wrong. But if you look at other observables like the average momentum fraction, the pion mass dependence, it's not 100% change, right? We're talking about things that may have a 10% change in the momentum fraction, which may have some impact here. And as we get to lighter pion masses, maybe our signal might not be as good. But we're trying to build up to that correct analysis of doing the right pion mass and extrapolate, or at least extrapolate to it.
So Brookhaven have no pion mass, right?
Yes, they've been doing, I believe they have some that are running at physical pion mass, yeah. And so we have some boxes too.
Right? So you have 300 and the Brookhaven have 100 or whatever, so.
Yeah, our results are consistent with the Brookhaven result as well. Like if we were to do just the lattice analysis, we're getting the same PDFs within comparable error bars with what they have too. So there are some slight changes that matter, but it's
Wait, for the pion,
for the pion PDF. If I were to plot
pion quark PDFs are the same in respective of quark.
they are consistent within error bars without changing the quark mass. So that has to do with how bad is our analysis and our ability to actually extract the things, as well as the true pion mass dependence.
Do people understand that? That seems
Well, if you go with the large Q-squared of the PDFs makes sense, then the quark mass becomes less relevant in effect. I think.
High energy on quarks and
Yeah.
massless. You really were doing this at
But this
is not high.
that's no.
It's a 1.5.
And it's a little tricky there because the PDF is encapsulating the long distance properties of the thing. You're then using it to understand what happens at high energy. But there are going to be pion mass dependencies. And they are going to have some non-trivial changes on the distributions.
I think part
But
of
we
it,
need to build up to it.
yeah, part of it is because you have some rules, right? You have momentum sum rules that give you a strong constraint too, right? So
Yeah, I mean, expect to see is
I
much
remember at early time the nuclear part PDF calculations for lattice actually really depend on the pion mass.
the average X does quite a lot once it goes under
the valence
but
peak, right? Sometimes move to the right.
But I believe the pion is not as dramatic in the effect, but it is something that we wish to push towards as we get to it, right? It is, we want to have everything under control, right? We want to get the best and realistic PDF out at the end of the day. But this is a long program.
I think really what you need to do is when you do combined analysis, add an A and pi squared like correction.
Well, we need two different pion values to do that. Currently, this is one pion
No,
mass.
but even right.
So,
So if you did it with the experimental, the phenomenological extraction, the lattice extraction, probably you would see no improvement because it just gets soaked up by this.
So in this, we did include some systematic errors, which that would be, if we had the sensitivity, we wrote about this saying, we would add in exactly that manner. But we added in some, including deviations with large separations, as well as the A over Z errors if your discretization is too short. And that definitely changed the impact. If we didn't include these, the improvement that I'm claiming was much more. But by adding in some systematics, it's exactly as you say. But yes, we need to add in all of the systematics at the end if we want to really make the final analysis. But this is not meant to be the final analysis, right?
one thing. For this PDF, there is a difference in the perturbative order that is known on the experimental side and the lattice side. So the experiments are pushing this to NNLO or to 3NLO or
yeah, for this we kept it consistent, except for the Drellian data we tested. Do you do leading log resummation of the threshold logarithms? The matching for the PDF for the lattice is now known to NNLO.
It's not known.
It is now known to NNLO. So we have that, and so that can be used and applied.
Because something that is also relevant, I think, is that if you try this to NNO and NNLO, then there will be some data, but But really, it doesn't matter to get it more precise or whatever, because really, this is in the region where perturbation theory will.
Yeah,
I mean,
absolutely.
that comparing these two different orders will tell you
Actually,
what region this is.
Go
You don't need to
the
push
other
this one, okay?
this is changing the order in this analysis here. So I don't know. There's an orange band you can't see, then there's a green band you can't see.
You can just do
You're
two
gonna
hand.
you're gonna pinch.
Like
Think they're gonna.
Like your
Take
phone.
one. So
Yeah.
Oh yeah, look at that.
You have to hold.
Okay, well I have to hold it. Good.
Okay, I see.
Okay, so here we're varying the orders and what terms you're doing, and there are changes, as you say. We're going from yeah, so we go from one band, and if you see when they start doing the resummations, they're starting to become the huge scale variation as you get to low x as well. And so these are systematics that people are starting to understand and apply to these studies, and including us, but unfortunately not any of the ones that I'm highlighting here.
that was the coolest use of the TV ever.
All right. All right. Last thing was gluons. Jam has been analyzing the various contributions to the spin of the proton, right? So there are intrinsic contributions coming from the fact that quarks are spinning, the fact that quarks are rotating around, the fact that gluons are moving around, the fact that gluons are spinning. And in the Yaffe-Manhart decomposition, each one of these gets its own contributions to the total spin, which must be a half. Now, the delta G, the intrinsic gluon helicity, is the integral of the helicity distribution function, which can be described as the difference of the aligned and the anti-aligned gluons. So you imagine all the gluons going this way minus all the ones going that way. So if your parton distributions were number densities, these can't be negative. But it turns out, due to the properties of normalization, they can actually go negative depending on what your schemes are and what's going on there. And so what Jam did in this analysis here is that they removed this positivity constraint. So before they were only ever getting this red band, which is constrained in the large X region by the fact that it has to be less than the gluon distribution, which is a very small function. So when they remove this, they suddenly see a huge blow up in the large X region, exactly where lattice is sensitive, but they also see this additional negative sets of solutions that appear. And so we want to really try to understand what these functions look like, because if you suddenly have these negative distributions, you don't really know the integral of this function. You have no idea how spins are, how the gluon spin is being included. So we were able to calculate some lattice data up here, which is sensitive to this distribution. And if you look at this, which is before we combine our analysis, we see that this negative band really looks nothing like what the lattice data is. And so we were hoping this would be a good signal that if we were to add it in, and what we see is that there is a huge change in what this negative band looks like. And so this was interesting for a few reasons. For example, this negative band, if you were to then use it to predict what are Higgs production at RIC, you would get negative cross sections. Negative cross sections are bad. You shouldn't have that. If you were to use this band instead, they're very close, they're very small, but they're not negative. So that is an improvement over this analysis, which is a nice thing. But it still was not able to completely eliminate this negative set of solutions. Now, one thing that I think is very interesting about removing the positivity constraint is I personally like to think about these things in terms of the aligned and anti-aligned as something more physical. When you have positivity, you just get very small things, and just large X aren't contributing that much. When you violate positivity, these things turn negative, and this absolute value is bouncing back. There's some X value, according to this fit, where the gluons just don't contribute to the proton. There are just no gluons with that X value in some manner. And I think that's very interesting. Like, why should that be? But okay, so this is why I think that's an interesting thing to be looking at and trying to nail down. The other thing that happens in this analysis is if you consider the singlet distribution, which we didn't add data for, you see that it changes dramatically. Somewhere around here is where the lattice or the experimental data for the singlet distribution was cut off. And in this extrapolation region, you see the results change very, very much. And so this led to the next analysis that my JAM colleagues did, which is if you take all the same data you had, you take the lattice data, and you loosen one of the cuts that they had on the experimental results, only then can you start to constrain this positive X region enough to get to having the only positive sets of solutions back. So in this recent by Nicholas Hunt Smith, I believe they were added in, much lower final state masses in order to really reach to a larger region. So these are the different cuts that different experimental groups might be doing in order to get different answers, and it turns out changing this cut really mattered. Okay, good. So here are conclusions. We calculate PDFs. They're somewhat close to being right, it seems. And we're working on getting all of our systematics together, but there's more we can do. We can also attempt to understand this evolution of the distributions itself non-perturbatively from Lattice QCD. And these lattice and experimental analysis seem to be quite impactful in what we can learn about these distributions. So I went a lot longer than I wanted to, but thank you all.
Just final comment. So I don't know. I mean, I think Jan lost some credibility when they talk about the RT, right? I mean, I personally also talked to them many times. Suppose you do Higgs or even LC meson production in at a rate, you'll get a negative cross section.
Yeah.
They didn't do this. I mean,
they didn't use that as a constraint, yeah.
I mean, once you get a very negative, very negative, you could generate a negative cross section. And they didn't do this exercise. It's very simple, right?
Yeah, the philosophy of Nobuo was if you're not including the data, you don't know what's going wrong where that data is.
That's the answer to my question. But I mean, it's there, right? That's why Warner and other people put Higgs at it.
Yeah, right.
I mean, that's possible. I don't know. I just don't understand their logic. And to some extent, I think they lost a little bit of credibility on this. As a physicist, sometimes you have to be careful, right? Cautious of what you're going to statement you have.
That's just like demanding to add something like causality or something. Like, even if your data can't predict it, ultimately everything has to be causal. So a cross section has to be positive.
Has to be positive. That's true.
So that seems like a very.
I mean, but when comment is the reply is like what Joe said, I need a physical process. But come on, sometimes you can tune your energy, right? So you could reach that. For example, I just don't understand. What's the anyway.
Yeah, it certainly has been quite a controversial thing of the way they did this analysis, but they finally reached to this last thing where they added in the new experimental data, whatever it needed to do to tease things away that we're no longer talking about anymore.
Okay, you want to save some.
So, well, yeah, so hopefully.
What was the new data?
It was relaxing this cut, so allowing more data from the polarized JLab experiments, which have much lower final state mass. So you imagine in DIS, right, you're hitting the proton, it shatters and things go out, and the final state mass is this
getting into the resonant region.
Normally they cut off that data. So, I mean, to apply this data, they have to argue this over the hadron, parton hadron duality. Basically, resonance also kind of behave like a quark or whatever in the final state.
Hadron quark duality.
Yep.
For some reason, I thought the global fitting would like to use the 10 greater GeV squared, but some experimentalists like greater than just 4 GeV squared.
Oh, yes, GeV experiments are always useful.
Always for it. Yeah, I questioned them this a while. They say that.
Yeah, I don't know if you saw in the, I have the white paper of JLab up here, and the 12 GeV band, I think, was 2 GeV.
That's true.
Oh, no, it's not squared though. So this is a 4 GeV squared
Yeah, yeah,
bound. Yeah,
that's right. Inelasticity. This is very close to the threshold of resonances. The nuclear resonance is about 2 GeV. So assume that 2 GeV up is already quark. So
no, that's already have some resonance there. I remember somebody showed this, like they have resonance structure, but if you integrate the resonance region, they get almost a smooth curve.
That's what the parton, the quark duality, quark hadron dualities. But resonance structure, I thought, above 2 GeV is very small. Also up to 2 GeV. That's probably the justification for 2 GeV might be tough. I don't know.
And actually, thinking of the resonance structure, the hadronic tensor method is unique in that it can actually probe into some of these regions meaningfully, unlike what we've done.
If you wanna hear more lattice details, Joe's talking to us tomorrow at noon. If we're lucky in this room, we're unlucky in room 191, which
Who
is
knows what about.
by the door.
By the door, so
What was that, Wednesday?
And you're here till next Tuesday?
No, until
Thursday.
Till Thursday, okay,
Thursday.
so you can interrogate him
Just
tomorrow.
Yeah, I'm out.
Yeah.
Okay,
A lot of questions.
all right.
Yeah, it's a very complicated project with a lot of things.
Thank you.